Hello guys, welcome to another video of my new series lectures of flight mechanics and performance. Okay, so this is my first lecture in how the calculation and derivation of takeoff distance, and I am focusing on takeoff phase and finding the equations to evaluate the takeoff distance. Okay, so takeoff phase, the aircraft will begin to accelerate from ground borne to safe borne state. Okay, so it will begin in the ground and goes to some point over the ground. Let me make a quick sketch and I'll show you what I mean now. Okay, as you can see here in this figure, these two figures, I'll tell you what's the difference between these two. The first one here, if you can see, the distance is the takeoff distance. It's more longer than this one. Okay, if you can see here. Oh, sorry. This distance from this first point to this point. At this point, the aircraft, the lift will be is greater than weight, so the aircraft will climb. Okay, at this point, I mean this short distance here, if we say this is A and this is B, you can see here A is bigger than B. Why is this? Why this distance is less than this distance? Because here we use a conventional aircraft. I mean by conventional, there's no flaps, there's no use of flaps here. Okay, just normal wing. Okay, and this one we use flaps here. I'll tell you what's the purpose of flaps in the flight mechanics and the aerodynamics of the aircraft. So when we use flaps, because flaps, it has very great effect on generating lift force, so you can use flaps to eliminate the distance, the takeoff distance. And here we don't use flaps, so take a very distance, and we are trying to calculate this type of aircraft. Okay, this height here is the safe altitude to transfer from this takeoff state to next climb state. Okay, so it's around 50, or some reference you can find at 35 feet. Okay, so I made this quick sketch here to show you how to divide these stages into 3 stages. This is the runway, here this line is the runway, here's the aircraft, and this is a trajectory of the flight move. Okay, so if I make it in this point, the aircraft will be this way. Okay, it's the aircraft here. Okay, it will be here like now, and this altitude, as I said, this is a safe altitude, which as I said, it's around 50 feet. Okay, so if I made a tangent here, okay, straight line, straight tangent here, and this angle will be gamma, and this this aircraft, this first point, let's say O, and goes to some point here when the lift will be more greater than weight, and the aircraft will lift the ground here. So let's say, sorry, it's not this point, this point, yeah, this point. So this point, so as I said, it will begin from the rest and goes. It will accelerate the aircraft until it reaches some point here. For example, the aircraft will lift the ground here at V lift off. We call this at V lift off. Okay, so we divide this. First segment will be, let's say, this one, first distance, and the second one will begin from here and goes to this point. Okay, and this segment to this segment will be S2, and the lift of the segment here from here to 50 when the aircraft reach this point, from here to here, I mean from here to here, will be S3. Okay, so we have 3 distance. We need to calculate each part of this distance. Okay, so the first one is S1. The aircraft will be like this way here. It will go in this ground. We have thrust force and drag force, and we have lift force, and we have the weight. Okay, let's see two figures here and tell you what will happen. Okay, so first the aircraft will accelerate along the runway. This aircraft will accelerate along this runway, okay, until it reaches the speed at which there's enough lift force is generated to overcome the aircraft weight. Okay, so this aircraft will accelerate until it reaches this point here. Let me mark it in red here. Mark it here. This point. So the aircraft will accelerate until it reaches this point. At this point, the aircraft, there's many lift force are generated, and it will be more than the weight force. This we call this at this velocity here. This velocity, the lift off. Okay. Then the aircraft will begin an airborne. This will begin to flight here. Okay, until it reaches this, from this point to this point. This point will be, the aircraft will be in safe altitude and will go to next segment of climbing phase. I'll discuss in next lectures. Okay, so as I said, this from this V lift off to this point. How we will find this point here? Because we made this tangent here line and cross this this line here, and from the V lift off to this point, this is S2, and the lift of the segment will be S3 from this point to safe altitude, which is H. Make a straight line here and you find S3. Okay, so now we need to discuss this third stage. Okay, third stage, we need to find S1. As you can see here, you can pretend this not aircraft, you can see it as a car, because it will be run in this straight line in the runway. So it's ground airborne. It's a ground borne, I mean. Okay. One point I need to mention here that we are talking about conventional aircraft. We are talking about conventional aircraft or conventional takeoff and landing. Okay, this type of aircraft. So what makes this aircraft? What's the special in this aircraft, or what makes this aircraft? It has some specific feature. This aircraft, the thrust to weight ratio will be a moderate, will be around 0.3. Okay, the division, if you divide the thrust force over the weight, it will be moderate, it will be around 0.3. Okay. So as I said, we need to find this S1. Okay, so we have, as you can see here, we have thrust here, thrust force. It will go this way, and we have drag force if the movement will be this side. So we have thrust force of the of power plant system, and we have drag force due to the medium. It's a function of velocity, of course, the drag and the lift, and we have here the lift force and we have the weight force. Okay, and we have this reaction because we have some wheels here, so we have two reactions. We can make it okay, I'll write it, I'll draw it again, and we have this mu r. What's mu? It's friction force, and r this reaction. Okay, let's make it again here. Okay, so we have this thrust. We say that the movement will be this side, so we have thrust force and drag force and lift force and weight, and there is other force here we called r, which is reaction. Okay, and we have, because the movement will be this side, so we have another force here will be mu times r, which is the friction force and this reaction. Okay, now we use the Newton's second law of motion to find this S1 at the end. Okay, so the Newton's second law of motion will be summation of forces will be equal to m times a. Summation of force acting on this body will be equal to the mass times the acceleration, all in this x direction. We have this only x direction. Okay. Okay, so we have thrust minus drag minus mu times r will be equal to m times acceleration. Okay, as I said, this is the mu is the friction force on this reaction, and this the mass of the aircraft, and this the acceleration. Okay, Okay. Now we divide by m here. We make some calculation. T over m minus drag over m be mu r over m will be only the a, and we know the a, the acceleration will be equal dv by dt, the first derivative of velocity with respect to time. Okay, so it will be equal dv by dt. Okay, now this will equal to, let's rearrange it. This thrust over m minus drag over m minus mu friction force over m. And what's r? What's the reaction here? If you see the reaction, let me take the first picture here. If you can see, if you see here, if the movement in this way, this is the movement side here, and you can see here is the mu times this one is the reaction. It will equal to this. Okay, so r will be equal mu times w weight minus lift. Okay, when the aircraft will be at rest, this we have no lift here, so it's equal only weight, so it's very big. R will be very big. When the aircraft starts to generate more lift, this this quantity will be eliminated and will goes to zero as the aircraft run along this runway until it will be zero. Okay, when the aircraft will be in the air. Okay, so times r, as I said, it will be equal weight minus lift. Okay, will be equal to dv by dt. Okay, now we make some other calculations here. We just make it very quickly. T over m, d over m minus mu w over m minus mu l over m will be equal dv by dt. Okay, we know weight will be equal m times g. G is the gravity, acceleration, and this is the mass of the aircraft. This is the weight of the aircraft. So from here we have m equal w over g, and we substitute back here, so we get 1 over m t minus uw minus 1 over m drag minus mu lift, mu times lift force will be equal to dv by dt. How we get this? We take 1 over m here, so we have only t minus I move to this part here, so we take 1 over m, so we have left mu times w minus 1 over m because this drag minus, so it's very straightforward and you can review it by yourself. Okay, when we reach this point, so we apply these relations here. Okay, so we get this equation g, gravity, b thrust over w minus mu minus gravity d over w minus mu lift, mu times lift over w will be equal to dv by dt. All right, now we go to another point. Okay, so we get g t over w minus mu minus g over w, take a w from this, we left d drag minus mu lift, have dv by dt. Okay, now g t over w minus mu minus g over w, this weight and this the gravity, acceleration. So the drag here, we know the drag and lift. Let me write it here. The drag force in another color, drag or d, it will be equal to half rho v square s times cd. Rho is the density of what? Of the medium, which is air in this case. Okay, v velocity, s the surface area, and cd is the coefficient of drag, and lift force be equal to half rho v square s times cl. This coefficient of drag and this coefficient of lift, and this is the same as here. Okay, So we substitute here in this relation rho v square is times cd minus mu half rho v square is cl, okay, will be equal to dv by dt. Rho half rho s, okay, cd minus mu times cl, okay, times v square is equal to dv by dt. Okay, if you see here, this is a coefficient during the takeoff phase, during the first segment of takeoff phase. This is a, and this part here is another coefficient. All these are coefficients here, okay, because we are talking about sea level. The aircraft is in sea level here, so rho we took in sea level, density of the air at sea level, okay, for that specific area, okay, and all of these are constants, so we take it as b. So we have dv by dt will be equal to a minus b v square. We have here v square, so it's function of velocity here. Okay, we make some calculations here. If we take dv over a minus b v square will be equal only dt here. Just multiply this, go up, and this goes down. Okay, and if I multiply this side dt, okay, by ds over ds, I didn't make anything here, and we know, I'll use this one here, and we know the velocity will be dv ds, by dt. So this quantity here will be 1 over v. So dv over a minus bv square will be ds over v, okay. So we multiply, we make some arrangement here, we left off with ds equal to v over a minus bv square will be v over a minus bv square times dv, okay. Now we need, don't forget, we need only C1, S1 here, the first segment, so we'll make some integrations here. We integrate both sides here, we integrate this side and this side from 0 to S1, and this from 0 to V left off, okay. If you differentiate this, the denominator here, this 0 and this 2b v with respect to v, I mean, when you differentiate this, minus differentiation of this minus 2b, okay, minus 2bv. So we have v here. If we multiply the first one minus 2b and divide 1 over minus 2b, I didn't make anything here, so this will be S1, this is the first integration here, S1 equal to 1 over minus 2b, okay, natural logarithm of a minus bv square. From the table of integration you find it here, and you need to substitute v and v left off, 0 and v left off, so S1 will be minus 1 over 2b ln a minus bv square, or v left off, I mean, because we substitute this v square minus ln a, okay. This is the first segment. We calculate the distance here. Okay, now we move to the other segment, which is S2, as I said here. So we calculate this one, the S1, and we need to calculate S2, which is it's more easier than this one. It's not very long. Okay, let's begin. So now, after we finish the first segment, so we are going to calculate the second distance here, S2. Okay, the second distance, the aircraft will go from here, this point, to this point. Okay, let's say it here. So we have thrust minus drag will be equal to m times a, which is the Newton's second law of motion. So now we are calculating the second distance, S2. Okay, so we use the Newton's second law of motion, which is summation of force will be equal to m times a, and from the equation of motion we know that v square equal u square plus 2as. This from classical mechanics. If you find a from this equation, you got v square minus u square over 2s. Okay, this will be equal to acceleration a. V is the final velocity, this initial velocity, and is the distance between the two velocities here, and a is the acceleration. Okay, so we substitute this into this one. Okay, so now we substitute this acceleration here in this equation. We have t minus drag will be equal to m mass times v square minus u square over 2 times s. Okay, this is 2. Okay, now we have here s2 equal to m over 2 times v square minus u square over t minus d, thrust minus drag. Here we need to know what is v equal to the final velocity and what's u, the initial velocity. Here, as you can see here in this point, the initial velocity for S2 will be v lift off, and this one at this point, at the end point, this is the final velocity. Let's say it's v2. Okay, so we substitute all these here. This, as I said, this v2 and this v lift off. Okay, substitute here, so we got s2 m over 2 v2 square minus v lift off square over thrust minus drag. Okay, so this v2 and this is 2, the second segment, and usually v2 equal to 1.1 v lift off. Okay, for conventional aircraft. Okay, so let's compute S3, and we end the takeoff segment. Now S3 here is from this point to this point. Let's compute S3 now. As we make here, I'll draw this again, this part. The aircraft, for example, reach this point, this h, safe distance, this distance is h, this one is h, and we have here thrust, lift, which is perpendicular to this line, and this drag, and we have this, which is pointed downward here, it's w, the weight, and we have here this angle will be gamma. So we have this here. If we need to make the components of weight along these two vectors, along these two axes, we have here w cosine gamma, and we have here with the drag w sine gamma. Okay, now we use the Newton's second law of motion. The summation of force will be equal to mass times acceleration. So we have thrust minus drag minus this one will be equal to m times a. So thrust minus drag minus w sine gamma will equal to mass times acceleration. We assume the velocity here along this trajectory will be constant, so we have zero acceleration. So we have this assumption, zero, because steady climb aircraft. Okay, so we have this part here goes to 0, and if you can see here, sine gamma from this from here, from this equation, we have sine gamma will be equal to thrust minus drag over w. Okay, let's write it down. From this equation we can make theta force theory, if we see this gamma, sine gamma will be this over this, so T minus D, and this one's W. And we have here, if you use Pythagoras law, we have W square minus thrust minus drag square. Okay, if you find this tan gamma here, tan gamma will be thrust minus drag, this over W square minus thrust minus drag square, and tan gamma at the same time, if you see here, will be H over this. Tan gamma is this over this, and this one what is S3, so tan gamma will be H over S3, and we need S3 here. It will be equal to H over tan gamma, and will be equal to H times W square minus thrust minus drag square over T minus D, square root of these two, of this term. Okay, that's all. We found S3, so the takeoff distance will be, S total will be just S1 plus S2 plus S3. Well, we'll take an example for this one, for real aircraft data, and we'll use also MATLAB for solving these kind of estimation problems. Thank you for watching. I hope this video will be helpful for you. If you have any questions and discussions, please leave it in the comment section below, and thank you for watching.